Hi, Sander here. We're at the airport of Dübendorf, and behind me is one of the world's most interesting cars. In this video, we're going to find out all about it.
Some people like racing cars. Some people like electric cars. Some people like robotic cars. Today's mighty machine is all of the above. In this video, I will show you AMZ Castor, the 2023 autonomous electric racing car of ETH Zurich competing in Formula Student. Discover the insane engineering behind it, how many of its parts are manufactured in-house, the architecture of its AI-driven Autopilot, and get to know a few members of the team working day and night on this outstanding vehicle. So strap in and buckle up, as we are about to enter the world of AMZ Racing. Let me give you some context. This is ETH Zurich, the Swiss Federal Institute of Technology in Zurich, a well-known institution. For decades it has been amongst the best universities in the world, and even Albert Einstein himself has lectured here. Students studying engineering sciences at ETH will be given a choice in their third year. Either continue with the lectures or sign up for a so-called focus project. The idea of those projects is for students who have at this point had 2 years of lectures to get to work on practical engineering challenges with their own hands. And this is where the airport of Dübendorf comes into play. In the so-called Innovation Park, students get to crash dive into topics like robotics, mobility, aviation, aerospace engineering, materials, and much more by participating in a focus project for 1 or 2 semesters and figuring out how to build an actually working thing on their own, based on what they had learned in class. In here, you will find teams building rockets, the famous electrical plane E-Sling, or our today's star, AMZ Racing.
Yeah, then welcome here at AMZ Racing in Zurich. My name is Daniel and I'm this year's team lead of AMZ Racing. And yeah, we are here in our workshop next to our 2021 car. Maybe in general, what is AMZ Racing? AMZ Racing is a student association here at ETH Zurich, and we are competing in Formula Student. And Formula Student is the biggest student engineering competition worldwide. There are like 600 to 700 teams existing over the whole world, and yeah, we are one of them competing only in Europe though.
Starting from 2007, AMZ has developed a racing car every year, with Castor being their 2023 car. Since 2010, all of them are electric.
Every year we have a complete new team of students, mainly bachelor students in their third year. So this is our core team working full-time. So we have 16 people from ETH plus 4 people of Luzern working in the core team. And then since 2017 we also have a driverless team making the car run autonomously. And there we have around 15 master students. Most of them in the past at least were robotics students, and in addition we have nearly 20 or around 20 freelancers. Those are just students, most of them in their second year, working part-time in the project and maybe joining the project full-time the year after.
At first, this may seem like a lot of people working on a vehicle that looks like a go-kart. But don't let its appearance fool you. Castor is a true high-tech beast. It is currently charging for a first test run with the latest iteration of the artificial intelligence that the driverless team is developing specifically for it. For the test run, some aerodynamical parts prone to break in a collision have been replaced by cheap wooden dummies. After all, no one knows whether the software is going to work or if the car is about to go out of control. Castor is equipped with a variety of sensors, amongst them a camera, a LiDAR, and a ground velocity sensor, providing vital data on the car's current position, surroundings, and slip behavior as it drifts around the curves. While Abiram is checking the onboard status, let's get to know some more members of the team.
Hi, I'm Jonas and I'm Swiss. I come from Lausanne, but I'm studying here my master in Zurich at ETH. I'm studying math, and I wanted to have a more concrete project, so that's why I joined AMZ. I'm doing driverless simulation here, and also I work a lot about testing. So my role is basically to tell the others what they did wrong.
I'm Yorgos, I'm from Cyprus, studying robotics at ETH. I'm at my master's degree, and I'm doing velocity estimation at AMZ which basically takes measurements from sensors for acceleration and velocity. And I filter these measurements because they are noisy, and I give them to the rest of the pipeline for the controllers to adjust their parameters and for predicted position of the car while running to localize the car more easily.
My name is Bartosz, I come from Poland, and in AMZ I'm doing simulation for driverless part of the team. So basically I create a simulator where other people can test their algorithms. And in terms of field of study, I'm doing data science on University of Zurich.
My name is Asbjørn. I'm Norwegian, and I'm responsible for the control of autocross. So mainly I use time here to look at how the controller is doing and try tuning some parameters to get it to go the fastest as possible.
The team is currently preparing a test run for their newest Autopilot software.
Right now, we are one of the first times we're driving this discipline with this new car, and we're just trying to figure out a set of tuning parameters that work with the new car. Yeah.
What is the discipline about?
So it's basically like we've got an unknown track, and the car is supposed to navigate through this unknown track as fast as possible. Also while creating a map of its environment so it can use it for the next discipline, which is driving around this track where it knows the track but doing like 10 laps.
It's all about cones, blue on the left and yellow on the right. The car must navigate them on its own. To get a rough outline on how this works, let's ask an expert.
Alright, hi, my name is Stan. I'm a master student at ETH, and I'm part of the team lead of the AMZ driverless team. So how this thing works is the car has a bunch of sensors all over places that we take that sensor data as input to our stack, and then the stack makes a decision that is then transferred to the car, basically saying what the car should do. And the first step in the stack is so-called perception. Perception takes the visual data from camera and from the LiDAR and gives us the locations of the cones. On the camera side, we use machine learning algorithms, object detection algorithms that basically take camera image. We run the image through a machine learning algorithm that gives us bounding boxes for the cones. And then on the LiDAR side, we have point clustering algorithms that basically look for clusters of points in the LiDAR point cloud, and we know that those clusters will be cones, the precious cones that we're looking for. Then that data is merged, given then confidence intervals and so on to decide what is actually a cone and what maybe is not necessarily a cone, but the pipeline has decided to classify it as a cone with some certain probability. And as output, we have the final so-called cone area, which is just the locations of the cones. So once we know where the cones are, so how our track and environment looks like, that data is given to the next module, which is estimation. Estimation takes the data from the velocity sensors to estimate the state of the car, so how fast we're going, what is our acceleration, how much grip we have. Additionally, estimation takes the data from perception to create a map of our environment, and what is even more important, localize the car within that map, so where we currently are within the environment that surrounds us. And estimation also creates a path. So we know the blue cones are on the left side, we know the yellow cones are on the right side. What estimation can do, it can already estimate the path that we should follow. Not necessarily say the exact path that we should follow in order to optimize lap time, but it can create the boundaries of the track. The next thing that has to be done is decide what we're gonna do, right? So where are we going? So controls runs different optimization algorithms in order to make the optimal decision on where we should go. So how much steering angle we should apply, how much throttle we should apply, if we should brake, and so on. And that is basically the output of the pipeline. So a car command that is then sent to the electronic control unit, and then the command is sort of applied to the vehicle. And this entire thing runs in a loop over and over again. And this loop allows the stack to drive the car autonomously, and it runs at around 10 hertz, so 10 times per second.
While the car is charging, the team uploads the software and runs some checks over Wi-Fi through an SSH connection. The computer piloting is located in the car itself. It runs ROS, the robot operating system.
The high-level pipeline, so our algorithm and everything was working quite fine with this car, Bernina, which is last year's prototype. And right now we're struggling a lot with some more low-level stuff. For example, we switched the communication protocol between the VCU, the vehicle control unit, and the computer box, which is the computer inside the car. So before we had communication via CAN, and now we switched to Ethernet and using a UDP protocol, and nothing was working anymore. So we're trying to fix this. We reduced the buffer size of the messages and stuff like this, reduced the frequencies of our controller, so we reduced a bit the performance, but it's still fine. And right now we are struggling with powering the computer box correctly.
The combined complexity of the hardware and software of this vehicle is enormous, and every aspect has its challenges. On the track, the Wi-Fi connection is cut and the car must operate on its own. Once it's cut loose, all the team can do is to press this button to trigger an emergency stop.
When I press this button or when this loses battery, the car stops immediately. With this one we're going to competition with, so we are very cautious.
Well, I heard. Now we have the front pressure check.
It must be quite a thrill to hand over the control of such a vehicle to an untested software you just wrote. And that's precisely what's about to happen now.
Okay, let's go. Okay, just come a bit.
So what happened in this test run?
So what happened? We have to figure that now, but we could smooth our control input. So basically before the car was shaking, now it's smooth, so we had an improvement. And then we probably have a localization error there where we hit cones, but that's what we're gonna figure out now.
The car has recorded its test run in great detail, and the team is downloading that telemetry data via SCP. On the laptop, this allows a precise reconstruction of everything the car experienced. Now the search for the needle in the haystack can begin.
So probably, as you could see in the video, one of the frame was moving a lot. That means we couldn't localize well. Our position is off, but our position estimated from velocity estimation sensor, not from the camera and the LiDAR. Because we don't have that many updates from the LiDAR, we have more updates from the sensor themselves, and the time we don't have update by the LiDAR, the frame is basically getting off.
Second run, double fun.
Back, come backwards. Distance.
Same curve, same trouble. After more debugging, the culprit is finally found.
So you've identified your troubles?
Yes, we had kind of a bad version control. That means someone else changed the parameters and we didn't notice, and that's why we're completely off. So we're fixing it at the moment.
You're basically reverting it to what you had before.
Yes, exactly.
But on a complex project like this is not as easy as just running git revert head. After struggling for a while, the team decides to contact the author of that part of code.
The torques get capped at 8, right?
Yeah.
But when we do multiply interval DC, we multiply it with 20 times TPTM max. And so if TPTM max was 1 before, what that means is that 0.5 throttle is actually corresponding to 10 Newton meters, but you just cap it at 8.
This is getting way too technical for the scope of this video. So while the driverless team is thinking hard, let's go visit the workshop where the car's custom parts are made.
So hi, my name is Philip. I'm from Zurich, and I study at ETH. I study mechanical engineering, and now in my third bachelor year, I'm doing the focus project at AMZ Racing. And what I did in this year was to develop the next generation of our own developed motors, the M12. And currently they're all in the car, all implemented, and until now it looks really cool. And I'm really eager to see how we perform in the next events.
So you built the motors in the car yourself?
Yes, exactly. So we're designing it, we're self-developing it totally on our own. We're simulating to see how much power we need actually from our constraints, and then we develop it and draw it. Then we get the parts from our manufacturing sponsors, but we build the stator and the rotor also as well, all together in here in Dübendorf.
Right now it's inside this casing for the motor test bench, but I mean here you can see the size of it, not really big, weighing 2 kilograms the motor itself. Our communication to the outside, and here we have the phases connected and the ground. Yeah, we have a resolver under there, and the resolver is measuring the angle of the rotor. And this then gets communicated to our power electronics, and we also have some temperature sensors, which is also communicated with this connector there.
So my name is Jan Stadelmann. I'm coming from Lucerne. I'm electrical engineer at ETH, and here in AMZ I'm developing our inverter.
Why do you build your own inverters?
Okay, in order to maximize points, no, it's like a whole big topic why we should build our own inverters, but in the end it's much more easy to actually optimize it to our needs. It's much more, with our own software, our own hardware, we can really get into the smallest detail to actually optimize our car and therefore our performance. And in the end, we just want to win the race.
They have also developed their own test stand, where 2 motors are physically connected. One runs and the other recuperates, keeping the levels of required power to something the grid can provide.
And inside of here we have also a torque sensor, where we can actually measure if the torques we want to apply actually are applied. We usually just test different steps. We first start very low with low power and low RPM, and then go step by step further to actually kind of test our limits and hope that everything is working as it should.
Remember that these people are just students from various fields of science. They have gained most of their practical skills right here, learning by doing. But there's more. AMZ even produces their own carbon fiber parts.
This is milled at the sponsor, and then we are getting this part, maybe sanding it down, and cut the carbon fiber here, and then laminate it by hand, and then using the autoclave to cook basically the part. And here, for example, is the crash structure, taking up all the energy when you are crashing in front into a wall. This also, for example, needs to be checked and certified by an institution, official institution. Concept-wise, you can do whatever you want, but it needs to be safe. And this is one of those parts that ensure the safety of the driver. There's a lot of simulation going into that part, while this is a lot of testing. You can see the carbon fiber crash structure in the front, and also the carbon fiber plate. And here this bulkhead, which should simulate part of the chassis basically. As you can see, it failed a bit. The screws weren't properly mounted. So this was a failed test, but luckily afterwards we got one that was fine. With carbon fiber we can reduce the weight from, I think we save around 1 kilogram per rim on the car, and then it's undamped and rotating, so it's really a big performance booster, this part. And again, this part now weighs I think 840 grams, so and you can also hold it on your own.
Wow, that's super light.
And you can also have a look inside the rim. I mean, this is now an older rim, but here you can see what we are using. We have like carbon fiber, of course, and inside we have this core that we are also using for our wing profiles. We basically spread out the carbon fiber to increase the inertia and make it very, very, very stiff, while at the same time very light.
Hi, my name is Victor, and I'm this year's responsible for the composite manufacturing in AMZ. This includes mainly the chassis, the monocoque out of carbon fiber, but most of other parts that are made out of carbon fiber.
I'm Raphael. I study mechanical engineering, basically as everyone here. So I'm responsible for the CFD of the aerodynamics, but now I'm just also helping with manufacturing because yeah, that's what we need now.
So none of you is a material scientist?
No.
I'm Dimitri, also studying mechanical engineering. I've been responsible for the design of the whole aero package. Together with Rafi, we formed the aerodynamics module.
I'm Daniel. I also studied mechanical engineering. I'm part of the suspension module and was responsible for the wheel packaging, but now I turned into a aerodynamicist myself.
So what are you working on?
Yeah, I'm currently basically telling the computer how to cut the carbon plies, which we need later. They're just rectangles, so we then lay them on here. And in this case, this is just a unidirectional ply, so just in one direction the fibers, so that in this direction they are very strong, but in the other they don't really do anything. So these we put on the top, like on the outside where we can see them later, and beneath that we put these types of layers. Then we also have some more on the leading and the trailing edge of the wing. We have some more stronger carbon, so just so at the front and at the back we get nice finishes. And then in the middle we have a core, so just like basically a styrofoam but a bit more fancy, which we lay inside.
So this is how to make a part from carbon fiber. After choosing the appropriate kind of it, you take sheets of carbon fiber and put them into a hard object that will give them their desired shape. This process takes quite some practice to get the alignment right and make the layers fit neatly on top of each other. As you can see, there are two shapes being laid out, one becoming the top and the other the bottom of the future part. In the middle, the core is then inserted.
That's customly cutted Roatel core, so that's a trademark material. I don't know what it is exactly. It's quite light, but yet over a bigger area it's quite stiff too. So it's ideal. It gives our wings almost the same weight as if they would be hollow, but they're much more stiff.
The problem with this material is that it deforms very easily, so extra care is required when handling it. The challenge is to carefully wrap it in carbon fiber and then insert it between the two shells. Another challenge with carbon fiber is that you should not drill it.
Yeah, so we have the form in which we stick in those pins. We should then define the position of those holes, and so we have the exact position in our final part. Then when the part is done, we will take out the pins, and then we don't have to drill the holes. They are already there, and they are in the perfect position where we want them to be.
Now it's
pretty much permanent.
So you won't be able to lift it.
Wait. Yeah.
Yeah. Good. So it's good.
And but now we're actually doing the vacuum bag for the one of the rear wing profiles.
Then this whole assembly goes into the vacuum bag, where it gets to the big autoclave in the other room, and then it gets cured for a couple of hours, and then it's done. And the outcome should be a wing like this, if everything goes well.
Here you can see the difference between a well-manufactured carbon fiber part and a not so well-manufactured part. So the big difference is the process was the same, but with this part you see now there was a manufacturing error when doing the vacuum bag.
And so mid-curing process, the vacuum bag burst, and so then we did not have such a well-bonded curing process.
The piece is carefully wrapped in tape to avoid sharp edges ripping the vacuum bag open. After inserting it in the bag and sucking the air out, the whole assembly goes into the autoclave, which is basically a very fancy and huge pressure cooker. This will fuse the fibers into a single wing in the coming hours. I've been here for a few hours and I've grown pretty hungry. They told me I could get food at the pizza automaton. Wait, the what? Well, this place is just full of science fiction surprises, and the pizza is surprisingly good. So how is the driverless team doing? They flip the car around to see if the same problem arises going the other way.
Could you press the reset button?
No, I can't.
Okay.
Or maybe if it's not a emergency, we can try. Can you bring me this?
It says it doesn't want it, it's just changing and you run again.
Ah, okay.
I'm ready to run again.
You ready to launch?
Yeah.
Whoa!
Yeah, I don't know.
Okay, I'll try directly.
I launch now. So time seems to be. Yes, it was that. Then no, it's still the stopping AX. Told you.
This is weird. Make it more.
More frames? Wouldn't that mean less? Can't we make it?
No, more frames means more cone, but more fault positive.
Yeah, so it removes. It's what I've understood.
TA off is less
cones.
I thought you then disregard less cones, which you see because
Yes.
they don't.
Okay. If you have smearing issues in tight corners, switching off PCA. Do we have smearing issues?
They
remove the amount of frames. It said it.
We don't see anything in tight corners.
Without
Can we give a call to Abby?
No, he's sleeping. Don't call Abby.
Okay.
What do you need to know?
More cones.
How much sleep did you get?
And the last 72 hours, approximately 12 hours.
How many hours of sleep did you get?
Six and a half. I think that's good enough.
Around 4, 5 this night. I woke up at 4:50 and slept at midnight. 4?
That's a pretty good night. If you get 4 hours, it's a pretty good night.
Oh yes, the stakes are high, because AMZ is usually among the best in competitions. Daniel proudly shows their trophy cabinet full of prizes, including some trophies built from old Formula 1 parts, like an actual F1 nose, or one of the first electric boost motors from Formula 1. In fact, AMZ entered even the Guinness World Record list in 2016 with the fastest acceleration to 100 km per hour in just 1.513 seconds. Hi, future Sandro here. You know it takes me months to edit these videos, so while I was filming this in July, I'm still editing and it's November. But the good news is I have some news for you. Namely, back in July there was a second car that I was completely not allowed to film, top secret, and now, of course, the secret has been revealed, so I can tell you that car is called Mythen again, which is actually an older car from 2019. And this car was taken apart and remodeled by a team of former students who were also part of AMZ, but then came together again this year and rebuilt the Mythen car to break another world record. So this happened completely in parallel, same place, but different team, different car. And you may have seen the Tom Scott video about this. Of course, they managed to accelerate the car from 0 to 100 in less than 1 second. But I'll leave that story up to Tom Scott. Let's go back to July 2023, where the Custard team is struggling and fighting hard to get their car ready for the upcoming races. There is still a lot of work left to do, but their time is up as the hardware team takes over in the evening, taking the vehicle apart and working on it at night. To win a race, everything must be perfect. Even a thing as trivial as a faulty connector can cause the entire car to malfunction and the race to be lost. There are so many aspects to consider. An adjustable rear wing to master the air, a hugely complicated suspension to master the road, which is called a
modes decoupled suspension. And how that works is that under each push rod we have is basically a hydraulic cylinder that is connected here, and we can connect all these cylinders in a way that we don't have one spring damper elements for each wheel, but we have a spring damper element for different kind of modes. So one of them would be roll motion in a corner, for example, and I can simulate that. If you now look at the roll warp element and I push the car to the side, this is basically roll motion. On the other hand, there's warp, where the front and rear axle are moving against each other, and this is not damped at all. So if I just take one wheel, you can see that this rocker here is moving freely.
The reason why we do warp decoupling is so when we, for example, drive over bumps, such as, for example, here, all our wheels remain in contact. And here you can see with an older car, the car from 2016, now we're going to drive over this bump, and you can look at the wheels.
This newer car has the decoupled suspension, and unlike the older one, never loses contact to the ground.
This is a system that was developed here in-house at AMZ, and which would not be allowed in any other or in most of the racing series that exist. First of all, because we're using hydraulics, and the other thing is that we are connecting front and rear axle. But from the student, you can be quite free and experiment with stuff like that. So I think it's quite a good opportunity for students to come here to learn a lot and then be really creative in maximizing our performance.
And I guess you're wondering what future Sandro has to say about that performance. And the results are pretty impressive indeed. 9 times first place, 4 times second place, and 3 times third. A total of 20 trophies was won, with a dominant success in Switzerland and second place at the most important race in Germany, making Castor the most successful AMZ car in the past 5 years. And with that, it's high time for me to say thank you so much to the AMZ team who have spent so much time with me in this very busy period of theirs. With special acknowledgements to Stan and Daniel who have made this video possible in the first place. Also a big thank you to my Patreons, Max, Adivote, John, Peter, Jura and Alex. If you would like to support my independent work as well, the link is in the description. Well, with this, I bid you goodbye and thank you for watching. I hope the amount of detail was to your liking. So, see you in the next video and have a great day. Bye bye.